Could we detect dark energy in the lab? When will Sagittarius A star start shrinking? And could we build a space telescope like we built the space station? All this and more in this week's question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Carl Fulmer 1767. We've obviously been unable to find out exactly what dark matter and dark energy are. Is one of those easier or harder to detect than the other? We hear about dark matter detectors, but are there dark energy detectors? So we don't really know which is going to be easier to find, whether it's going to be dark matter or dark energy, but dark matter is the one that we've known about for close to 100 years, while dark energy is the one that we figured out back in 1997. So dark matter has had a head start, and there have been a lot of experiments done here on Earth to try to search for dark matter, as well as astronomical surveys looking for the presence of dark matter out in the universe. And it's the astronomical surveys that have been a lot more successful. They have gone and looked out into the universe and they've seen where the concentrations of dark matter are. They can detect all of the gravitational lensing and really map out the amounts and concentrations of dark matter, see how it separates from clouds of gas. And there can be whole galaxies that seem to be made almost entirely of dark matter, while there are galaxies that seem to have almost no dark matter. In the lab, things have been a lot less successful. People have come up with a range of experiments to try and search for dark matter, to try and, if it is a particle, then to detect the presence of that particle. And sort of most famously, there have been searches done with the Large Hadron Collider, where they've attempted to collide particles together, try to have particles show up that match some of the characteristics of what they're looking at for dark matter. But there are a lot of other things. There are detectors that are deep underground that are trying to measure the presence of dark matter particles passing through their experiments and things like that. Dark energy, right? This is that mysterious force that is accelerating the expansion of the universe. And once again, all of the evidence for dark energy has come from the astronomical observations. And so astronomers have looked out, they've measured the distance to type 1a supernovae and found that they're farther away than they would expect them to be. And that is due to this kind of mysterious force that's accelerating the universe. It picked up about, say, 7 billion years ago and has been accelerating the universe ever since. And this idea is old, right? The idea that there is some kind of cosmological constant, some sort of outward force that comes from the very nature of space-time itself, that if you have a cubic meter of space, that you get rid of all of the matter, all of the energy, you're still going to be left with something. And so the blandest explanation for what dark energy is that it is literally just when you get more space, you get more energy by having more space. But there have been some ideas to try to test out exactly how dark energy works in the lab down here on Earth. And what you're really looking to do is test gravity. You know, we know how gravity works thanks to Einstein and other people to an enormous level of accuracy and precision. But there is still a lot of unknowns. It's crazy, right? Einstein made all of these predictions about gravity thanks to relativity, and yet still astronomers haven't fully confirmed all of the predictions that he made. So I'll give you one. One's called the equivalence principle. And this is this idea, that you take two objects of different masses and you drop them in a gravitational field, they're going to fall at the same speed. And that experiment was done on the moon, where you've got, was it a feather and a hammer, and they dropped them at the same time and they fell at the same speed. And so according to the math, theoretically, two objects in the exact same gravitational field should fall together. And so experimenters have tried to demonstrate this in the lab. It's one thing to just get the math, but you actually want to perform the experiments to show that this is true. And people have sort of, to the best lab equipment that they could possibly come up with, they haven't been able to sort of prove that it's wrong. And then in fact, there was a mission that was launched into space back in 2016 called Microscope. And this mission was essentially in orbit, in free fall. It was testing how two masses would be free falling under the Earth's gravitational field. And what they found was that the equivalence principle holds. And they were able to measure it down to a level of accuracy of 10 to the minus 15. And that sounds impressive, right? Like 0.000, 15 zeros followed by a 1. The problem is the dark energy is much, much weaker than gravity. And that sounds kind of crazy, right? Because, you've always heard that dark energy is the vast majority of everything that's in the universe. What is it? 60-something% of the universe is dark energy. And then the rest is mostly dark matter and then a little bit of matter. Well, that's because when you have a lot of empty space, you get a lot of dark energy. But in small, very sort of tight spaces like near the Earth, gravity is going to be the thing that's dominant. And so although that microscope experiment was good, you would still need about 3 or 4 more orders of magnitude in accuracy to get to the point where you could detect some kind of deviation from what you would expect from gravity. And that would be the influence of dark energy. So there's been other experiments that have been done here on Earth. You've probably heard of something called the Casimir effect, where you've got 2 plates and you put them really close together, and then you sort of measure a force on those plates as essentially particles are not being able to appear in between those plates. And the plates are being pushed together by the particles that are outside the plates. And so people have proposed that you could take those Casimir experiments, and you could take them to space and try to see if you could detect weirdness that may be coming from dark energy as well. And then an idea that I really like is called atom interferometry. So you essentially take individual atoms and then you watch how they move in free fall. And because with larger objects with more mass, it's really hard to detect the influence of dark energy and things like that. But with an individual atom, the least amount of mass that you can constrain and track its movement, or even have an atom in free fall in space, then maybe you can start to detect the presence of dark energy. So yeah, scientists have absolutely thought of lots of experiments to try to test for dark energy. They've run a bunch so far, and none have been able to detect the presence of dark energy. But that's not a surprise, because in any sort of small cubic meter of space, the amount of dark energy that you're going to be experiencing is very little. And yet there's going to be a bunch of astronomical missions coming up. You've got Nancy Grace Roman, you've already got the Euclid mission, and then of course we've got Vera Rubin. A lot of these are going to be doing these large-scale surveys of the universe and try to detect what presence dark energy had at different points in the age of the cosmos. I'm sure you noticed the Stargate planet name that appeared above my shoulder. Of course you did. You're eagle-eyed. You see this kind of thing. Good attention to detail, they say. But what is that about? That is a way for you to vote, for you to tell us what you thought was the best question of the week. And so the winner of last week's best question was from Anonymous. Will you ever cover theories that don't have a Big Bang origin? So thank you, Anonymous, for asking the question. Thanks to everybody who voted. Now, we're going to put one of these Stargate planet names for each one of the questions of this episode. We'll put them down in the show notes so you can get a reference. And then when you ask a question, or just in the comments, put the question that you thought was the best. Just put the keyword, the code word, and we will count them up and we will celebrate next week. Burhai 1. Why is it that we see the same constellations throughout the year? Should we not be seeing different stars between summer and winter? It's funny, you're exactly right about the thing that we should see, which is that we see different stars between the summer and the winter. And that's exactly what we see. So we don't see the same constellations throughout the year. We see different constellations, but it depends on where you are on planet Earth, because the Earth's poles are pointing at various constellations. So I live in the northern hemisphere, and so we have directly above the Earth's north pole is Polaris, the North Star. And the constellation of the Little Dipper sort of wraps around the North Star. And then you have the Big Dipper, which points at the North Star, and it is also up there. And Cassiopeia is another one that's relatively close. And so throughout the entire year, those constellations are just going to be going around and around the North Star, and they're visible all the time. For me, sometimes the Big Dipper is upside down. Other times it is right side up. Who knows what's right side up and upside down in cosmos. But then other constellations, as you get farther and farther away from the North Pole, then we can only see them for part of the year. And in fact, it's because the Earth is orbiting around the sun. And so the sun is in one set of constellations during our summer. It's in the opposite set of constellations during our winter. And if you go out on a regular basis, you become familiar and accustomed to as the constellations change over the course of the year. So we're in early fall right now, and that means we see the fall constellations. So we see things like Taurus. We can see the Pleiades start to rise. If you stay up really late, you can see Orion come up. And then we'll shift into the spring constellations, Virgo, Aries, things like that. And then we get into the summer constellations. And that's where we see things like Sagittarius and Scorpio, and then back into fall. And so no, the constellations totally change. And then when you're in the southern hemisphere, then you can see certain constellations directly above that pole, and they don't change. They just, same thing, shift around the pole. But no. And in fact, that's one of the really cool things about sky watching, is that the sky looks different every single night of the year. It slowly changes, and you can just kind of feel how the constellations are shifting. And that tells you that we're on this ball that is spinning in space, that is moving around the sun. It's just this kind of visceral understanding of what's going on. Raul Gagna. In a recent episode, you highlighted how CMBR photons feed black holes. Apparently, even for a black hole of just 6 solar masses, Hawking radiation will not exceed the CMB contribution until the CMB drops to 1.5 K. When will Sagittarius A star start shrinking? Will all stars in the Milky Way and local cluster have already died by then? All black holes are evaporating. And this is this idea of Hawking radiation. And in fact, it might be that all mass is evaporating, that you're evaporating, I'm evaporating, Earth's evaporating. It's just that we evaporate very little compared to what a black hole will do, as the most extreme side of this. And so the problem with black holes evaporating is that it can only really start to lose mass once they stop gaining mass. And they're gaining mass all the time. Obviously, in the beginning, we've got all of the stars and planets and gas and dust that the black holes are vacuuming up. But eventually, all of those ready sources of fuel run out, and then the black hole is left. It's like starving, and all it's got is just individual particles of hydrogen that happen to have remained in the cosmos, and they find their way into the event horizon, and the black hole is able to nibble on that and stay alive. And then when all of those particles don't come by anymore, it's still being fed by the cosmic microwave background radiation. These are the photons left over from the beginning of the universe. And so they are still going to continue to feed and provide energy to the black hole, which, is the equivalent of mass, and that allows it to keep going. It's not until about 100 billion years from now when the background temperature of the universe will be so cool that the evaporation of the big black holes like Sag A star will start to take over. But this process is incredibly slow. There's a lot of mass. And so it's been estimated that black holes won't lose their mass for a 10 to the power of 100 years. So let's say 1 followed by 100 zeros. And that is a long, long time from now. So although the most massive black holes will start to evaporate in this sort of 100 billion years from now, it still will take just an insane amount of time before they're fully gone. Joker of all trades, can we build a space station observatory? In my wildest imagination, I see Voltron, but instead of limbs, it has a main module and moving telescope arms. Is a practical version of this possible? So there are some concrete plans to build sort of what you're talking about. Now, not the Voltron of space telescopes, although I agree that would be awesome and I think is worth doing purely for the memes. But when you think about the largest kinds of telescopes that can be launched into space today, you're limited by the size of the rocket fairing that you put your telescope in, and you're limited by the launch capacity of the rocket. And so the heaviest rockets out there before Starship, but when you think about something like, say, the Ariane 5, it could launch, say, a 10,000 kilogram space telescope, James Webb, which had to fit within a 5-meter fairing. And James Webb was able to fold out like origami and become a 6.5-meter telescope out there in space. If you use something like the Space Launch System, you could maybe build a folding telescope that could get you out to 15 meters. If you use something like Starship, maybe now you're building a telescope that can fit within a 9-meter fairing, and then it could fold out to be something more like 20 meters. And that's amazing. Like, that would be very big. But you're exactly right. When you think about something like the International Space Station, a modular space station, could you just launch all of the parts into space and then assemble them into a telescope? And instead of being limited by what can fit within one rocket launch, why can't you just launch a whole bunch of modules and start to piece them together? And so this is something that's called on-orbit construction. And this is an idea that's been floating around NASA for a couple of years. And it's sort of shifting into the inevitable department that the limits, the kinds of science cases that astronomers are wanting today, the kinds of observations that they want to make, the largest telescope that you can fit within a fairing just isn't big enough, that you need to go bigger. And so you could imagine some future version of a telescope. You've got the main part of the telescope that is like, has the power, has the electronics, and has a couple of robot arms kicking out the side of it. And then various components are launched, like the solar wings, and then it is able to bolt on the solar wings, and now it has more power. It's able to grab, say, the primary mirror and have it be in segments, and then it could assemble. Maybe it could crawl around and assemble all the segments of the primary mirror. And then each one could be, say, the size of James Webb. Each one could be, say, a 5-meter mirror that fits within a 5-meter fairing, and then the robot takes them and slots them all together and builds a mirror that's maybe 30 or 40 meters across. There's kind of no limit. And so, this idea of on-orbit construction is going to be the next, really what's going to be required. And because we have the International Space Station that prove that you can launch piece after piece after piece, and you can deploy them and construct them in orbit, I think there's a lot of really well-known pathways that engineers can go to try and make this a reality. And then the next thing that I really like is the idea not only of on-orbit construction, but actually on-orbit manufacturing. So what if instead of launching all the bits and pieces in various rockets, you launch a 3D printer? And the 3D printer, all it does is just spits out trusses, right? From aluminum or titanium or plastic or whatever out in space. And then it just extrudes it like a spider. And then you've got a truss. And then you can put, say, one side of an interferometer on the end of a truss. What about ideas for using liquid telescopes or liquid mirrors, where you could sort of carry some kind of liquid into space, and then you can, while it's in space and you're not experiencing the forces of gravity, you could start to spin the thing out, turn it into a lens maybe, and then you could have it solidify in space once it's done. So there's a lot of great ideas that can be done in space. It's just a matter of shifting from the old way to some new ways of building telescopes. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Gordon Proctor, Jim Burke, Mikkel Dunkar, Tomek, Sean Patterson, Barb Silver, Whiskey Alpha, Kathleen Thompson, Jesse Perbix, Sgr 173, Michael Mazinski, Major BS. Join the club at patreon.com/universetoday. Ellen Nelson, from our point of view, we never see an object cross the event horizon of a black hole. Do we not see an aggregate of objects there? So what you're describing is the fact that when an object falls into a black hole, it's falling into a very powerful gravitational field that causes time dilation. And so, it starts off, it's falling, it seems like it's moving at normal speed, and then it seems to look like it's going slower and slower, and then eventually it seems to pause right on the surface of the event horizon, and then it just fades away, redshifts and fades away from our perspective. But, you're asking, like, would you just see a whole bunch of things, all the silhouettes of all the stuff that have fallen into the black hole at various times? And like, maybe, if they fell in reasonable amounts of time, then that's what you would see is a sort of history of the things that had recently fallen onto the event horizon of the black hole from our perspective. So yeah, you could sort of You know, you could see all the explorers who thought that it would be cool to go and explore inside of a black hole, and you could sort of see, you know, the more recent version where they're screaming, and then the sort of the older version where they're screaming, but now they're screaming in slower motion than even the older version where they seem to be just paused screaming. And now they're starting to shift into the red. And then there's like someone looks like a ghost screaming, but just barely visible because they've shifted into the radio waves from our perspective. Santiago T. Even when interstellar travel becomes a reality, how would communication work to another star when you have to target a moving object for your transmission? You're exactly right that you would need to target your spacecraft that you're going to try and communicate with. And the problem is that the spacecraft is going to be moving. And if it's like moving on an interstellar velocity, then it's going to be moving at 20% the speed of light, or 10% the speed of light, maybe 99% the speed of light. How do you communicate with that? Well, if you know that it is going 99% the speed of light, you know exactly how fast your spacecraft is going. And so you send your message where the spacecraft is going to be when they receive it. And it's a math question, it's a trigonometry question. But, if you're a civilization capable of building a spacecraft capable of going 10% the speed of light, 20% the speed of light, 99% the speed of light, you are also capable of doing the math so that you can send a tight beam to your spacecraft. But when you send transmissions in space, they widen out. And so, ideally you'd be able to target your spacecraft with a very directed laser transmission so you can send communications back and forth. But the size of the laser when it arrives at the destination is going to be pretty large. And so you don't have to be as accurate as you think you might be. Rock Hopper, the Prime Directive, should it apply to Mars? What are your thoughts? Yeah, I think if we detect the presence of a industrial civilization on Mars and they have yet to develop warp drive technology, we shouldn't try to contact them. We shouldn't let them know of our presence. But I mean, I don't think you're actually talking about the Prime Directive in the Star Trek specific way. You're asking about us contaminating the surface of Mars. What kinds of safeguards should we take to make sure that we don't wreck the biosphere of Mars with our filthy Earth bacteria? And this is a very serious question. Up until this point, we have sent spacecraft to Mars that have almost certainly got Earth life on board, but they've gone to places that don't have access to liquid water. The people building the spacecraft have done as good of a job as they can in sterilizing the spacecraft. And so the amount of infection from Earth life to Mars is probably very, very low. But when humans arrive, we're covered in bacteria, we are breathing it out, viruses, all kinds of stuff. And so that stuff's going to get around on planet Mars. And it's kind of inevitable. We know that Elon Musk and SpaceX people are planning on sending missions to Mars in just a couple of years. And within a couple of years after that, they'll probably have people on board. And eventually there'll be a city on Mars. And so the question really is, if there's life on Mars, is it accessible to Earth life in a way that we could affect it, that we could infect it? And we don't know the answer to that question yet, right? And so it's really hard to find out the answer to that question. Like, how do you know if there's life on Mars that's at risk from being contaminated from Earth life if you don't go to Mars to try to study where there is Mars life, using even well-cleaned robots that are going to potentially infect Mars with life? And so do we just never go down to the surface of Mars ever again? We already have. So these are the questions. And so it's very much not this black and white issue. It's very much shades of gray that you have to say, what are the kinds of contamination risks that we're willing to make? What kind of precautions should we be taking before we expand our investigation into Mars? But, the Chinese are planning to send humans to Mars. NASA is planning to send humans to Mars. And like I said, SpaceX is planning to send humans to Mars. Yeah, I I think the cat will be out of the bag. The horse will have left the barn. Anyway, use the analogy that you like. Either we're going to infect Mars with Earth life, or we can't infect Mars with Earth life. Just won't work. Or there is no life on Mars to infect. And we're going to find out which one of those, but we're not going to be very careful about it. And I think we should be more careful about it. I think it would be really smart to take our exploration of Mars and be very, very careful about it. Because possibly one of the most important questions that we can possibly ask is waiting for us on Mars, which is that, is there life on Earth and is there life on Mars? And if there is life on Mars, does it share a common ancestor with Earth? And if it doesn't, then we will have another example of life forming completely independently. And so now we know that life formed on Earth and life formed on Mars, and that means life probably formed on Enceladus and probably formed on Europa. And there's probably an infinite number of worlds out there in the universe where life independently formed. And if we go to Mars and we find life, but we find the life has a common ancestor, that's exciting because now it shows that life was able to get from Earth to Mars. And chances are we're going to find life around the solar system will all be related. Big family reunion. But we could also just continue to search for life on Mars and never find anything. And that would tell us that life on Earth is actually very rare and special, and that we may not find life anywhere else in the universe. Eli in the Wolverine state. We have meteors from Mars that land on Earth. I would think that Mars has Earth meteors. The problem is that the gravity of Earth and the mass of Earth is dramatically higher than the gravity of Mars and the mass of Mars. So when you compare Earth to Mars, the gravity of Mars is 1/3 the gravity of Earth. And so it's much easier for you to be able to escape the gravity of Mars to be able to go to space. And the mass of Mars is 1/10 that of Earth. And so it's probably just a one-way journey, that there aren't a lot of places where Earth rocks will have been kicked off of our planet and gone to other places. But it's a lot easier to have meteorites arrive on Earth from Mars. In fact, we found meteorites on Earth from Mars, from the moon, from Vesta, right, which is an asteroid, but we haven't found any meteorites from Venus, which is kind of the same mass as us. And who knows? I mean, we haven't explored Mars really well yet, but I would be surprised if we found meteorites from Earth on Mars just because of that difference in gravity. Jeff Miller, why do comets have tails? Is there drag in space? I mean, I guess there's probably some drag in space. There's like the occasional hydrogen atom as your comet is moving through it. Some of the bits and pieces of the comet are going to bump into that. But no, the tail of a comet always points away from the sun. And that should tell you what the force is. So think about it, like a comet is falling down towards the sun and the tail is pointing away from the comet, away from the sun. But then as the comet goes around the sun, the tail is pointing away from the sun. And then the comet comes around and then begins its journey back out to the Oort cloud or the Kuiper belt or wherever it came from. And now the tail is ahead of it. And the comet is following the tail. It's always pointing away from the sun. And that's because the tail is caused by the solar wind, that you've got these particles that are streaming off of the sun and they are impacting the comet and they are causing the comet to vaporize. And you're getting all these particles that are going off and they're being carried away by the solar wind that's moving through the solar system. And in fact, there are multiple tails that comets can grow based on different kinds of solar wind material that's streaming off of the sun. You get different speeds, and so you get different tails on the comets. Laurent Laborde, is it possible for a black hole to explode or somehow stop being a black hole in some catastrophic way? Sort of. So we talked about black holes and how black holes can evaporate. And so in the beginning, for the, at 100 billion years from now, the evaporation process will begin. The black hole will start to lose mass. And then over that 10 to the power of 100 years, it will lose mass faster and faster until it gets to sort of the end game where the mass of the black hole, like essentially the heat that is coming off from the black hole, this is how we see the evaporation of the black hole. We measure its temperature, and the temperature will rise and rise and rise very slowly. You know, it'll be 3 Kelvin for a long time, and then it'll be 4 Kelvin, it'll be 5 Kelvin, and eventually it'll be room temperature. But black holes have to be very small, like the mass of a very small asteroid. And then they start to get hotter and hotter and hotter. Within a couple of days, a small enough asteroid, something that is, say, I don't know, the mass of a mountain, will completely evaporate. And then it will, sort of the last moments is it will be this flash of gamma radiation, and then it'll be gone. And so the catastrophic way is when it finally has almost completely run out of mass, it will heat up to the point that it will be incredibly hot, pumping out ultraviolet rays, pumping out X-rays, pumping out gamma radiation, and then it'll just be gone. Wrong way up. I know you're not an MD or biologist, but do you think the liver damage that space travel seems to cause will make it practically unlivable to go to and or live on Mars? So I'm not familiar specifically with the liver damage that you're talking about. We've done a bunch of reporting on brain damage and heart damage, vascular damage that comes from mostly radiation in deep space. And so if you're going to go on a mission to Mars, you're going to spend 9 months in a lot of radiation, about 200 times more radiation dose every day, right? So if you spend a day in deep space going to Mars, it's 200 days worth of getting radiation down here on Earth. And that's like a lot. And you're going to take that for 9 straight months on your way to Mars. And then you're going to be on the surface of Mars for either 3 months or 18 months, depending on which window you're going to wait to be able to return to Earth. And then you're going to make a 9-month trip back to Earth. And so you're going to spend 18 months in deep space, and then maybe another 1.5 years on the surface of Mars. Like, you're going to be eating radiation for about 3 years. We know that high amounts of radiation for long periods of time is going to cause damage to the body, both sort of problems with your brain, problems with your liver, as you said. It's going to cause vascular damage. We know it causes issues with people's hearts. And we're still getting to understand what kind of damage this is going to have. There's, every time astronauts return from the space station, people do a bunch of experiments on them to find out what kind of damage their cells had. There's lots of experiments that are being sent up to space. And the problem is that the space station doesn't receive as much radiation as deep space. It's protected by the Earth's magnetosphere. And there aren't a lot of experiments that are being done or have ever been done to find out what is the radiation load. The best information that we have is that there are radiation detectors on the Curiosity spacecraft. And so when it was traveling to Mars, it was measuring the radiation load, and now it still measures the radiation load while it's down there on the surface of Mars. And, its expert opinion is yikes. So anyone who goes to Mars is going to experience the short-term damage from the radiation, but then they're also going to be experiencing the long-term increase in cancer. And that's because you're just getting these cosmic rays that are blasting through your DNA, and they're going to increase the chance that you're going to get cancer at some point later in life. And for some people, that might be totally worth it. But for other people, they might be like, oh, God, there's only so much cancer I'm willing to risk having. But the good news is that in the medium term, there are solutions. And the solution is protons. You want to surround yourself with as many protons as possible. You want to get mass in between you and the rest of the universe. And it doesn't take a lot. A meter of water or a meter of rock in between you and space will remove that entire radiation problem. And astronauts are going to need to take water to space with them. And so you can imagine that they surround their habitat in water, and that keeps them safe, but it's also their drinking water. And don't worry, the water doesn't become radioactive. And then when they land on the surface of Mars, you dig under the surface of the regolith, dig into the ground, and you're protected from the radiation there. And then you just sort of really are very careful about the total amount of time that you have to spend out in the radiation. But it's interesting, in planning for a Mars mission, NASA looked at their requirements for how much radiation their employees, their astronauts are allowed to take, for like safety reasons. Is it like OSHA regulations? Anyway, and they just said they're out. Like, we can't send people to Mars and have them experience a reasonable dose of radiation, like we're going to break that. They're going to get more radiation than is expected. And I think, for some people, they're okay with that. Other people, they're not okay with that. The people who go to Mars know that they're going to be taking on incredible risk. And yet, the more time that we spend working on the technology, the more infrastructure that we have in space, eventually we can build protective habitats that people can go to and from Mars in a way that they don't have to experience very much radiation at all. And then when they get to Mars, they can go underground and they have to experience very much radiation at all. So these are all solvable problems. They just haven't been solved yet. All right, those are all the questions that we got this week. Thank you, everyone who both put their questions into the YouTube comments, as well as everybody who asked their question live here. We record this show live every Monday at 5 p.m. Pacific time. So if you want to be part of the live event, come and join us. There should be a notification somewhere here on the channel. And if you subscribe to the channel, click on the notifications bell, then you will get reminded when the live stream is about to happen. Like I'm sure like alarms are going to go off in your house. You'll have notifications popping up on your phone, on your computer, on your Steam Deck, and you'll be able to come and watch the live show. I'm going to talk about some of my thoughts with the Starship landing this week. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Barry Lake Roofing, David Gilton, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, ScienceWorldRecord.org, SpiderSwap.io, Stephen Filer Munley, and Vlad Shiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So this was an amazing week for space exploration, for spaceflight. We saw the 5th test of the SpaceX Starship and Super Heavy stack. And wow, like I've never seen anything like this, right? You see this skyscraper take off and then come back to Earth and maneuver and land with incredible precision in the Mechazilla, these giant chopstick arms on the launch platform. And it's just hanging there and it didn't fall apart and it didn't destroy the tower. And that was so great. And then not only that, but we actually saw the Starship go to orbit and return from the atmosphere. We saw once again the hot gases as it was starting to re-enter the atmosphere. And I was really worried about the launch flaps, but we were able to have, they had cameras on every single flap. And we saw in incredible detail that they were doing okay. And the Starship was able to make it back through the atmosphere. And then the sort of like the chef's kiss piece to resistance that we weren't expecting was that there was an actual platform floating in the middle of the ocean, exactly where they knew this thing was going to land. And it gave us a live view of Starship sinking under the ocean and exploding. And so like that, they clearly nailed exactly where they wanted to land. So, those were my initial thoughts. It was incredible, exciting. It felt great. A lot of my big nervous checklist boxes got checked. Now, I have done a collaboration with my good friends, Scott Manley and Marcus House, and we spend about an hour in great detail talking about the launch and our impressions and how things went and what comes next. And so if you want even more sort of detailed thoughts and observations, you should definitely check out that video. All right, we will see you next week.